Hi everyone, this is Mr. Lee. In this video, we are going to continue the discussion of distance and displacement, but we are going to be doing some two-dimensional vector addition. All right, let's begin. So what I want you to do is, before we start, pause the video, copy down these rules and instructions, listen to what I have to say, and then we're going to do a couple of example problems. So the first rule, you can only add x, y, and z vectors to other x, y, and z vectors, meaning you can only add x's to the x's, y's to the y's, and the z's to the z's. In the next slide, I'll go over exactly why that is the case. If your vector has x, y, and z vectors, you have to break it apart. Now, normally we'll be working in two dimensions, x and y, so that z1 won't come up as often. But just so you know, if there's a z vector, you do have to break it up. And you break up the x, y, and z components by using SOHCAHTOA trigonometry functions. All right, now you're going to combine all of the x's together, all of the y's, and all of the z's. Now, depending on the problem, you might have a lot of vectors to add, or maybe just one or two vectors to add, but it really depends on the situation. After that, you are going to be left with a sum total of the x vectors, a sum total of the y vectors, and a sum total of the z vectors. So you have to use the Pythagorean theorem to figure out the overall magnitude and direction of your finalized vector. Just like in the previous videos that we did, but now I'm going to show you an example problem using distance and displacement. Okay, so the reason why we can only add x's and the y's together is because vectors have a physical meaning, right? It represents something real to us. And so because of this, we have to follow the rules of reality. And those rules of reality denote what we're allowed to do. So for example, let's say you have a ping pong ball, right? I'll just draw a quick ping pong ball here. And let's say we push it in this direction, right? So this vector will be the push it. So let's say we push that ping pong ball in towards the right, but then all of a sudden the ping pong ball flies upwards instead of going to the right. Right now, that would be really strange. So that is the idea behind the x and the y vectors needing to be communicating with each other. So our expectations of reality is if we push along the x-axis, the object must move in the x-axis. Okay. If we push in the x-axis and it all of a sudden moves in the y-axis, that's really strange, and that doesn't work for us. All right. So that's the reason why vectors have to follow the rules of reality. All right. So at this point, make sure you get out your calculator. We're going to do two different methods, and it's going to require a little bit of math. Before we start, make sure that your calculator, if you're using a graphing calculator, there should be a button called Mode. And if you click Mode, there's a choice. So I'm going to write it up here. You have two choices. You're going to be either in radian mode or degree mode. So for physics, we always choose degree mode. And depending on your math classes, you will have to switch back and forth between radians and degrees. But for physics, we always use degrees. Okay, so now that that's out of the way, let's read this example first. And I encourage you to pause the video, have this example down in your notes. It does require a little bit more of copying down, but it's a good reference for you to have as you go back. Okay, so we have a squirrel and it runs in a zigzag pattern, right? So the squirrel first runs 8 meters along a 30-degree axis. So let's draw that first. And I didn't supply the images for you just yet, but here we go. All right, so this is, we'll call this distance A, runs 8 meters along the 30-degree axis. Okay, remember that capital letter A is a subscript, so it goes slightly below the variable d for distance. And then the squirrel also runs the opposite, pivots, right? And pivots and runs 10 meters along the 60-degree axis. So let me show you the vector that we're going to be working with. So here, okay, this degree what we call this theta b is 60 degrees. And to make sure we have everything lined up, we're going to call this theta a, and we're going to call this here uh, dB is 10 meters. Okay, so that's the image. I'm going to copy and paste that below in order for us to do the work. We're going to try to follow the rules that you copied in the previous slides. But before we do that, I want to make sure that we get some practice in with the tip-to-tail method. Okay, so if we have this coordinate plane, let's make sure we have this coordinate plane here. Okay, now I know we're not going to dip into the negative y region, so I kind of just skewed my axis. The first vector I'm going to draw is dA. So we have dA here, and this is theta A. And then they pivot, and they go like this. I'm going to draw the imaginary axis there so that we can imagine that this is still a right triangle, dB right here. Okay, so we have our two vectors. That's the tip-to-tail method, and the resultant vector would look like this. So remember, this resultant vector, this is your displacement. Okay, now the question says determine the distance and the displacement. So the distance is pretty easy to find because remember, all you have to do for distance is add up the actual length of travel. So let's do that math below. So the total distance is equal to dA plus dB. Now the reason why I'm showing you the formula method first is I want us to get into the habit of writing out the formulas for the more complicated problems down the road, where if you set up the problem in variable form, we can rearrange them and solve for the unknown variable a little bit more easy later down. So we have 8 meters, and then we have 10 meters, and we just have to add them up. So our total distance, remember that fancy E looking symbol, okay, that's sigma, that's math symbol for total, is 18 meters. And hopefully you got that one correct. All right, now for the trickier one, we have to find the displacement. So in order to find the displacement, what I'm going to do is I'm going to take a look at each of these vectors, dA and dB, and we're going to break dA and dB down into its components. All right, so let's take a look down here. Let's do dA first. So for dA, we have 8 meters at 30 degrees, right? And so what we need to do is we need to break down dA into its x and y components. So whenever we do components, because they're not real vectors, right? They're parts of the vector, we always use a dotted line. That dotted line shows us that it's not real, it's imaginary, because the 8 meters is the actual length that the squirrel traveled. But these are imaginary vectors. So we're going to call this dAy, and we're going to call this dAx. And that A and the X are both subscripts, and the A and the Y are both subscripts. Okay? Now, I'm going to show you the math over here to find dAx. So if you remember SOHCAHTOA, you have to see which sides you have to find the unknown side, right? So I'm going to highlight it. If we're finding dAx, we have the hypotenuse and we have the adjacent side here. And we know that it's the adjacent side because this side of the triangle is touching this angle. Okay, so we have A and H. So that means we have to use COT. All right, so to find dAx, we say that, well, let me show you the official math way. So the cosine of theta is equal to dAx, which is the adjacent side, over the hypotenuse, 8. All right, and we know cosine of 30 is equal to the following. So what I'm going to do is I'm going to move this denominator here over onto the other side so that we're solving for our only unknown variable, dAx. All right, and at that point, I'm just going to plug exactly what you see into my calculator. And I encourage you to do the same so that we can check to see if we have the same results. So I got that dAx is equal to 6.93 meters. In physics, two decimal places, A-OK. All right, so let's go through the same process to find dAy. I'm going to do this in a different highlighter. So let's do pink. All right, so to find dAy, it is opposite of the angle. So we have a O and we have the hypotenuse. So we have opposite and hypotenuse. So we have to use a sine function. Okay, so sine of the angle is equal to dAy over the hypotenuse, which is 8 meters. So rearrange that. Once again, I'm going to take this denominator, multiply on the other side. So we have dAy is equal to 8 sine theta. And once again, I encourage you, pause the video, put this into your calculator yourself, see what you get. Make sure it matches up with what I have, and have 4 meters. No rounding there. Okay, now we're going to do the same thing at this point. I encourage you to pause the video and just see if your results matches mine. So we have dBy, and I believe this was 60 degrees. And if I plug that into the calculator, dBx is -5. And remember that negative means that we're going to the left. And dBy, we get 8.66. All right. So now we have our components. It's kind of all over the place. And so what I want to do is I just want to organize it over on the right. Okay. Now, I don't always do this, but it's definitely helpful when you're doing your work to make sure that everything that you do is as organized as possible. Okay. So my x components, we have 6.93 and we have -5. And my y components, we have let me label it correctly. So dAy is 4 and dBy we have 8.66. Okay, so if you remember the rules, after you break up the components, what you have to do now is add up the components. So 6.93 minus 5, we have the total dy as 1.93. Remember the squiggly line, that E sigma represents total, and the total for, this should be dx, excuse me, and the total for dy would be 12.66 meters. All right, so what we just did is we added up dAx and dBx, and then we added up dAy and dBy to find the components of this green vector here. So without having to measure anything, just by math, we found that this component right there has, or that vector has these two components. And so what that would look like, I'm going to scoot this over to the side, is, let's see. Oh, I didn't draw it correctly. So it actually turns out, let's see. Oh, no, I did. All right. This dBx is, or dx is 1.93, and this dy is 12.66. Okay, so at this point, we're almost done. We have to find the actual displacement. In order to do that, we use the Pythagorean theorem. Okay, always show your work. So we have the Pythagorean theorem is equal to 12.66 squared plus 1.93 squared. So if I plug that into my calculator, okay, once again, pause the video right here and see if you get your same results that I do. And I would save the rounding until the end. So if you round it like I did, you would get 4.47 meters as your magnitude for the vector for your displacement. So let's write that in. But remember, this requires a direction. So this theta right here, okay, once again, using SOHCAHTOA, I see that we have the opposite side that we found and the adjacent side that we found. So we can say the angle is the inverse tangent of 12.66 divided by 1.93. And once again, pause the video, okay, and make sure you get the same results that I do. If you do that, we get an angle pretty steep, 81.33 degrees. So this vector, okay, uh, that displacement vector is 4.47 and 81.93. So what that means is instead of doing a zigzag pattern, if the squirrel just ran 4.47 meters in an 81.33 degree angle, the squirrel would have ended up in the same spot. But the squirrel's trying to evade the hawk. All right. Now let's use the hat method. Now, luckily, the hat method takes into account of all the math that we previously did. Okay, and so it really depends on which method you like. I like using both methods, but let's try this. So I'm going to take a look up here. So those are, you got 4 and 6.93. So in order to use the hat method, we have dA, so it's a vector, and dA is 6.93 I hat plus 4 J hat. Okay, and I'm going to just put dB right below it because dB we have 4 I hat, and the excuse me, it should be negative 5 and 8.66. So this should be negative 5 plus 8.66. All right, so now that we have our vectors, right, so this method doesn't require us to get the triangle and like redraw it and all that because we just have those numbers, okay, and all those numbers came from the previous work that we did, but we add them up and we see that the displacement would be 6.93 I hat minus 5 I hat, so 1.93 I hat, which gives us the displacement's x vector plus 12.66 j hat. Okay, and if we use the Pythagorean theorem, which we did before, we found that the delta x is what is it? 4.47 4.47 meters at about 81 degrees. All right, so those are the two different methods. Even though the hat method looks a little bit cleaner here, it's only because we used the component method before to actually find those numbers. Okay, see you next time. Bye-bye.